Hello, I am back. I'm live. This is a study session where I'm going to be reading this tutorial chapter on PCA, which is the Principal Component Analysis, and this is kind of the engine behind machine learning and the statistics behind putting the pieces together. So we're gonna read this. This is just a simple study session, and we're gonna go from there. All right. So let's get started. Chapter 2: Background Mathematics. This section will attempt to give some elementary background mathematical skills that will be required to understand the process of principal component analysis. The topics are covered independently of each other and examples given. It is less important to remember the exact mechanics of the mathematical technique than it is to understand the reason why such technique may be used. And that is true. We see that with the SAS programs. As long as we understand, we can utilize our technology and use the right tools to get the results, but we have to be able to interpret the results. And what the results of the operation tells us about our data. So those are the keys. Not all of these topics are used in PCA, but the ones that are not explicitly required do provide the grounding on which the most important techniques are based. I have included a section on statistics which looks at distribution measurements, or how the data is spread out. The other section is on matrix algebra and looks at eigenvectors and eigenvalues, important properties of matrices that are fundamental to PCA. This is it's like kind of on the brink of, moving into some very high level abstract theoretical statistics, mathematics, and machine computer technology. So it's really interesting. There's not much out there on the topic, so a lot of people don't have the background or the fundamentals to really even understand the technical aspects behind this type of dry mathematics. I mean, you're talking about matrix algebra, right? In a matrix itself, we've been computing, single numbers like 3 plus 2, and 6 plus 10, or 4 times 5. But what if we change it from 4 to a huge array of numbers? Say we have 1, 2, 3, 4 plus another huge array of numbers like 5, 6, 7, 8. And so we're changing, instead of numbers, and transitioning into operating and doing arithmetic on matrixing, a matrix of numbers. And usually matrices can represent a data set or a spreadsheet, if you will. 2.1 Statistics. The entire subject of statistics is based around the idea that you having this big set of data, and you want to analyze that set in terms of the relationships between the individual points in that data set. I'm going to look at a few of the measures you can do on a set of data and what they tell you about the data itself. So there's the standard deviation, right? And this is more exploratory analysis. So if we have this huge set of data, we do need to understand like the 5-point summary, the deviations. What is the deviation? What does the deviation tell us about the spread of the mean, that the data points, how far away the data points from the mean, and what is the mean in the first place? And so these are the answers, and of course the variance stems from the standard deviation. To understand standard deviation, we need a data set. Statisticians are usually concerned with taking a sample of a population. To use election polls as an example, the population is all the people in the country. whereas a sample is a subset of the population that our statisticians measure. But the great things about statistics is that by only measuring, in this case by doing phone surveys or similar, a sample population, you can work out what is most likely to be the measurement if you use the entire population. Alright? And that's really inferring if you have a small little sample. If we study the nuances of a sample and we collect enough of those types of samples and we study them, we can now infer about the general population without ever having to gather the full population, because we know that statistically speaking we have boundary points. Alright? So yeah, in this statistics section, I'm going to assume that our data sets are samples of some bigger population. So there is a reference later in this section pointing to more information about samples and populations. Here's an example of a set. Well, I really wish they would have used commas to separate the values because it looks like a huge number. Actually, it looks like 1, 2, but it looks to me, if you look even closer, it's 1, 2, 4, 6, 12, 15, 25, 45, 68, 67, 65, and 98. They are not in order because of the 68, 67, and 65, but we almost had order. But there are a bunch of different values in there. So it says, so X is this set. It almost looks like an array, almost like a matrix. Anyway, I could simply use the symbol X to refer to this entire set of numbers. If I want to refer to an individual number in the set, in the data set, I will use subscripts on the symbol X to indicate a specific number. So, e.g., X sub 3 refers to the third number in X, namely the number 4. So X sub 3 is 4. Note that X1 is the first number in the sequence, not X0, like you may see in some textbooks. Also, the symbol N will be used to refer to the number of elements in the set. So there are a number of things that we can calculate about the data set. For example, we can calculate the mean of the sample. I assume the reader understands what the mean of a sample is. It is given by the formula X bar is equal to the sum of all x's, where xi is 1 to n, so the sum of all the x data points divided by n. Alright, sometimes we abbreviate this because we know what mean means so much, and oftentimes you'll just see x bar. X bar basically is the mean or the average. And all this formula is saying is that you add up all the numbers and then divide by how many numbers there are. Unfortunately, the mean doesn't tell us a lot about the data except for a sort of a middle point. For example, these data sets have exactly the same mean, but are obviously quite different. So we have 0, 8, 12, 20, and 8, 9, 11, and 12. And so basically what it says is that they have the same mean. However, notice how in this data set it's really like widespread. Like the range of the numbers go from 0 to 20. So it's like the actual range value is 20, whereas these range from 8 to 12, and they hover around 10. So the mean can only indicate a middle reference point, and it's not that robust. It does vary according to certain numbers. Like if I have a huge number, one single huge number, it could throw off the mean quite a bit. So it says, what is different about these two sets? It is the spread of the data that is different. The standard deviation, SD, of a data set is a measure of how spread out the data is. How do we calculate it? The English definition of SD is the average distance from the mean of the data set to a point. The way to calculate it is to compute the squares of the distance from each data point to the mean of the set, add them all up and divide by n minus 1, and take the positive square root. Then because it is a sample, we do have to divide by n minus 1. That's considered a degree of freedom. You have to take into account that the sample is not the true population. When we're calculating the standard deviation for the true population, we do divide by the entire number of n, the entire cardinality of the set. So little s is the usual symbol for standard deviation of a sample. I hear you asking, why are we using n minus 1 and not n? Well, the answer is a bit complicated, but in general, if your data set is a sample data set, you have taken a subset of the real world, like surveying 500 people about the election. Then you must use n minus 1 because it turns out that this gives you an answer that is closer to the standard deviation that would result if you had used the entire population than if you used n. If, however, you're not calculating the standard deviation for sample but for the entire population, then you should divide by n instead of n minus 1. For further reading on this topic, the web page such and such standard deviation in a similar way also provides an example experiment. And I think it's been shown mathematically that if you, for your standard deviation of sample, if you divide by n minus 1 every time, especially if your sample is sizable, your standard deviation will be a little bit more accurate. And that's it. And so they ran with it. And we want accuracy. And so here is a table calculating standard deviation. So we have two sets. We have one set 0, 8, 12, 20, and the other set 8, 9, 11, 12. They both have the same mean. So it's x bar minus the mean. The mean is 10, so we're going to take 8 minus 10 is negative 2, 9 minus 10, 11 minus 10, 12 minus 10. Square them, and now they're all positive. Add them up, divide by 4, and now take the square root of that 3.333, which is 1.8257. Okay? So the standard deviation of set 2 is 1.82, and the standard deviation of set 1 is 8.32. So it also discussed the difference between samples and population. So for our two data sets, the calculated standard deviation is table 2.1. And so, as expected, the first set has a much larger standard deviation due to the fact that the data is much more spread out from the mean. Just as another example, the data set 10, 10, 10, 10 also has a mean of 10, but its standard deviation is 0 because all the numbers are the same. None of them deviate from the mean. Variance is another measure of the spread of the data in a data set. In fact, it is almost identical to the standard deviation, other than you do not take the square root. And so it says you will notice that this is simply the standard deviation squared, and both the symbol s squared and the formula s squared is this symbol for the variance of a sample. And so we have three data sets. It says find the mean, the standard deviation, the variance for each. And obviously they probably want you to do this by hand. If you do have technology, by all means, use technology. I think I have technology here. I'm going to try. See if I can. I don't know. Okay, so here we get into covariance, right? So we're going to be measuring the variance of these together. Okay, so there's a special formula. You notice when we have one set to calculate the variance, we would just do the difference of each bar square and divide by the total number to get the variance. But to actually get the covariance, it's a special formula. It's a little different now. Okay, the last two measures we have looked at are purely one-dimensional. The data sets like this could be heights of all people in the room, marks for an exam. However, many data sets have more than one dimension. Okay, and the aim of statistical analysis of these data sets is usually to see if there is any relationship between the dimensions. For example, we might have as our data set both the height of all the students in class and the mark they received for that paper. We could then perform statistical analysis to see if the height of a student has an effect on their mark. Standard deviation and variance only operate on one dimension, so that you could only calculate standard deviation for each dimension of the data set independently of the other dimensions. However, it is useful to have a similar measure to find out how much the dimensions vary from the mean with respect to each other. This is really deep. Often we were doing tests on the difference of means or the difference in variance, where we would do the one dimension calculations, the other dimensions calculations, and subtract them. But now we're considering the two data sets to be of the same, and they're just a different dimension. And so we have to redefine how we calculate what would be considered a variance and what we call a covariance. So covariance is such a measure. So covariance is always measured between two dimensions. If you calculate the covariance between one dimension and itself, you get the variance. Wow. So if you calculate the covariance between one dimension and itself, you get the variance. That would be a nice little exercise to do. So you take your set and duplicate it, calculate the covariance, and obviously it will suffice because that's why we square it. We square it, so yeah, that shows it right there. There's the proof. Done. Case in point. Covariance is always measured between two dimensions. If you calculate the covariance between one dimension and itself, you get the variance. So if you had a three-dimensional data set, x, y, and z, then you could measure the covariance between x and y dimensions, the x and z dimensions, and the y and z dimensions. Measuring the covariance between x and x, y, and y and z would give you the variance of x, y, and z, respectively. The formula for covariance is very similar to the formula for variance. The formula for variance could also be written like this, where I have simply expanded the squared term to show both parts. So given the knowledge here, the formula for covariance would be covariance of x, y would be that, where we're taking the product of the difference between the means of each set and we're dividing it by n minus 1. And I think there's some assumptions about n, that the two sets are of the same size. Otherwise, that formula would not hold true. So, a plot of the covariance data showing positive relationships between numbers of hours studied against the mark received. Let me go to that chart. So they just because they just talked about the chart, so it's a good idea to understand what they're talking about before we read. So we have this chart. It's the number of hours that you have studied and the marks that you have received, and that's our data set. And so obviously this would be considered two dimensions, and each hour is connected to a mark, so obviously they have the same size, and we're going to calculate the covariance. Now we have the average of each, and the average is needed to calculate the covariance. We calculate it, add them all up, multiply it out, and we get the average. and that's it. We get this huge value, 104.54. Okay, so now let's read. It is exactly the same, except that in the second set of braces, the x's are replaced by the y's. Then, that is, for each data item, multiply the difference between the x value and the mean of the x by the difference of the y value and the mean of the y, and add them up and divide by n-1. How does this work? Well, let's use some example data. Imagine we have given the world a collective two-dimensional data set, so we've asked a bunch of students how many hours in the total that they have spent studying and the mark that they received. So we have two dimensions. In the first, we have the h dimension, the hours studied. In the second, we have m dimensions, the mark received. And figure 2.2 holds my imaginary data and the collection of CovHM, the covariance between hours of study and mark received. So what does that tell us? The exact value is not as important as its sign, whether it's positive or negative. So the fact that it's positive, and it's much positive, that is valuable. So if the value is positive, as it is here, then that indicates that both dimensions increase together, meaning that in general, as the number of hours of study increased, so did the final mark. If the value is negative, then as one dimension increases, the other decreases. If we had ended up with a negative covariance here, then that would have said the opposite. That is, as the number of hours study increased, the final mark decreased. And that, in the last case, if the covariance is 0, that it indicates that the two dimensions are independent of each other. The result that mark given increases as the number of hours study increases can be easily seen by drawing a graph of the data, as shown in figure 2.13. However, the luxury of being able to visualize data is only available at 2 and 3 dimensions, so the covariance value can be calculated between any two dimensions in a dataset. This technique is often used to find relationships between dimensions in higher dimensional datasets where visualization is difficult. You might ask, is cov xy equal to cov yx? Well, a quick look at the formula for covariance tells us that yes, they are exactly the same, since the only difference between cov x and y and cov y and x is that this product is replaced by that product. And since multiplication is commutative, 3 times 4 is equal to 4 times 3, which means that it doesn't matter which way around I multiply two numbers, I always get the same value. So it doesn't matter what set we choose to be our first set, as long as we have two equal sets, the covariance will be the same. Now let's look at those two values in the figure. So we've had the data, imaginary data set, we've calculated the covariance, and now there's 2.21. Let's look at the other sets. Where's it at? Where's it at? Okay. It's gone. It's gone. It's gone. Okay. Well, we got 2.2. So now we're going to talk about the covariance matrix. Recall that covariance is always measured between two dimensions. If we have a data set with more than two dimensions, that there is more than one covariance measurement that can be calculated. For example, from a three-dimensional data set, dimensions x, y, and z, you could calculate cov xy, cov xz, and cov yz. I think that's a typo. It's okay though. In fact, for any n-dimensional data set, you can calculate n factorial over n minus 2 factorial times 2 factorial different covariance values. Okay. So it's basically 3 choose 2, or n choose 2 every time. So we're selecting 2 combinations out of all 3, and so 3 choose 2 is definitely 3. The combinations x and y doesn't count, because the covariance of y and x is the same as x and y, so we don't have to count that. There's 6 different permutations, but 3 combinations. That's why we divide by the other 2. Divide out the duplications. A useful way to get all the possible covariance values between all the different dimensions is to calculate them all and put them in a matrix. I assume in this tutorial that you are familiar with matrices and how they can be defined. So the definition for covariance matrix for a set of data within dimensions is C m by n, and big C. Okay, let's just read it out. So Cm by n is equal to Cij, comma Cij equal to the covariance of the dimensions of I and the dimensions of j. Where Cm by n is a metric with n rows and n columns, and dim x is the x dimension. All that is an ugly looking formula. It says that if you have an n-dimensional data set, then the matrix has n rows and columns, so it is a square, and each entry in the matrix is the result of calculating the covariance between the 2 separate dimensions. In general, e.g., the entry on row 2, column 3 is the covariance value calculated between the 2nd dimension and the 3rd dimension. Okay. An example will make up the covariance matrix for an imaginary 3-dimensional data set using the usual dimensions x, y, and z. Then the covariance matrix has 3 rows and 3 columns, and the values are these. So it's 3 by 3, x, y, and z. 1, 1, term 1, 1 is xx, and we take the covariance of xx like so. All of the different possibilities in a matrix. Now, we already know that these values will be the same. So once we find, and these will just be the variance of x, y, and z, and these values will be the same as well. So to calculate that, we create a huge matrix with all the possibilities. Some points to note that down the main diagonal you will see that the covariance value between the one dimension and itself, these are the values that for the dimension. The other point is that the cov AB is equal to cov BA. The matrix is symmetrical about the main diagonal. So some exercises, it says work out the covariance between x, y, and z, or x and y dimensions in the following 2-dimensional data set, and describe what the result indicates about the data. Oh, this is just your basic. The covariance would just simply be, you simply just calculate that one pair of x and y. Now calculate the covariance matrix for the 3-dimensional set of data. Well, this is a little different now. We now have to calculate every pair, and so we'd have to calculate the covariance of every single pair. It's kind of like a table, a matrix table there. Okay. That's pretty interesting. All right. What we'll do We'll go on a little bit further and then we will probably take a little break. We have three different sets here, set X, set Y, set Z. We're going to define all of those different covariances between the three different sets. So the covariance of those, which would be, the first entry would be the covariance of X. The next one would be the covariance of X and Y. And then the third entry in our matrix would be the covariance of X and Z. And then we move to the second column, so it would be the covariance of Y and X, which was what we've already calculated, then the covariance of Y and Y, and then the covariance of Y and Z, and then Z of X, Z of Y, and then Z of Z. Once we do that, we'd be done. And I'm assuming that there's some technology that we can use to calculate a covariance matrix when we have a set of data. So it's not, we don't just plug these values into a matrix. It's this set, and each set has in the number of values in each set is 3, whereas the number of values in each set here is 5. But this is 2 dimensions, and this is 3 dimensions. It's just listed in this manner. This section serves to provide a background for the matrix algebra required in PCA. Specifically, I will be looking at eigenvectors and eigenvalues of a given matrix. Again, I assume a basic knowledge of matrices. Now, eigenvectors and eigenvalues allow us to equate equations. You can also solve a basic system of equations by knowing the eigenvalues and eigenvectors. It's where you get linear combinations, but you want to know what those unknown values are, so that, you know, matrix A times some value plus matrix B times some value will give you matrix C. And so it is an algebra problem for sure. So we have this problem. So we're given that this 2 by 2 times a 2 by 1 is 11/5. Now you multiply this by 1 times 3, so 2 times 9 is 11, and then we just 1/3 times 2, 1. That's 2 times 1 plus 3 times is 5. And then we also have this, that 2, 3, 2, 1 times 3, 2 is equal to 12 over 8, which is equal to 4 times 3 over 2. So I guess what we have showed, what we have showed, I'm not going to take the determinant of that, even though it's 4. Example of one non-eigenvector and one eigenvector. So we have this, we're multiplying out, we get 2 over 8, and that's equal to 4 times 3 over 2. So 4 times 3 over 2 will equal 12 over 8. It's just an example here. And let's look at another one now. 2 times 3 over 2 is equal to 6/4. And then if we do 2, 3, 2, 1 times 6/4, we get 24 over 16, which is 4 times 6/4. Example of how a scaled eigenvector is still an eigenvector. Okay. So as you know, you can multiply two matrices together provided that they are compatible sizes. Eigenvectors are a special case of this, so consider the two multiplication between a matrix and a vector. In the first example, the resultant vector is not an integer multiple of the original vector, whereas the second example, the example is exactly 4 times the vector we began with. Why is this? Well, the vector is a vector in two-dimensional space. The vector 3, 2 represent an arrow pointing from the origin 0, 0 to the point 3, 2. The other matrix, the square one, can be thought of a transformation matrix. If you multiply the matrix on the left by of a vector, the answer is another vector that is transformed from its original position. It is the nature of the transformation that the eigenvectors arise from. Imagine a transformation matrix that, when multiplied on the left, reflected vectors in the line y equals x. Then you can see that if there were a vector that lie on the line y equals x, its reflection itself. Its reflection is itself. This vector and all multiples of it, because it wouldn't matter how long the vector is, would be an eigenvector of the transformation matrix. What properties do these eigenvectors have? You should first know that eigenvectors can only be found for square matrices. They have to have the same dimensions. And not every square matrix has eigenvectors. And given an n by n matrix that does have eigenvectors, there are n of them. So given a 3 by 3 matrix, there are 3 eigenvectors. If, of course, they exist in the first place. Another property of eigenvectors is that even if I scale the vector by some amount before I multiply it, I still get the same multiple of it as a result, as in figure 2.3. This is because if you scale a vector by some amount, all you are doing is making it longer, not changing its direction. So you're changing its magnitude, right? Lastly, all eigenvectors of a matrix are perpendicular at right angles to each other, no matter how many dimensions you have. By the way, another word for perpendicular in math talks is orthogonal. This is important because it means that you can express the data in terms of these perpendicular eigenvectors instead of expressing them in terms of x and y axes. We'll be doing this later in the section on PCA. Another important thing to know is that when mathematicians find eigenvectors, they like to find the eigenvectors whose length is exactly 1. This is because you know the length of a vector doesn't affect whether it's an eigenvector or not, whereas the direction does. So in order to keep eigenvector standard, whenever we find eigenvector, we usually scale it to make it have length of 1, so that all eigenvectors have the same length. Here's a demonstration from our example above. So 3, 2 is an eigenvector, and the length of the vector is the square root of 3 squared plus 2 squared, square root of 13. And you know, you can verify this in the Pythagorean theorem, right? And the xy plane, you can represent this as a vector starting from the origin that terminates at the point 3, 2 in the plane. There's a 1-to-1 correspondence between the points in the plane and the vector space, two-dimensional vector space. So we divide the original vector by this much to make it have a length of 1. So if we divide 3, 2 by, you could multiply it by 1 over root 13, you should do, right? Then you get this. Now, how does one go about finding these mystical eigenvectors? Unfortunately, it's only easiest if you have a rather small matrix, like no bigger than about 3 by 3. After that, the usual way to find the eigenvectors is by some complicated iterative method, which is beyond the scope. If you need to find eigenvectors of a matrix in a program, just find a library that does it all for you. A useful maths package called NewMat is available at there, and further information about eigenvectors in general, how to find them, and orthogonality can be found in the textbook Elementary Linear Algebra. Eigenvalues are closely related to eigenvectors. In fact, we saw an eigenvalue in figure 2.2. Notice how in both of those examples the amount of which the original vector has scaled after multiplication by the square matrix was the same. In that example, the value was 4. 4 is an eigenvalue associated with the eigenvector, no matter what multiple of the eigenvector we took before we multiplied it by the square matrix. We would also get 4 times the scale vector as our result. So you can see that the eigenvectors and eigenvalues always come in pairs. When you get a fancy programming library to calculate the eigenvectors for you, you usually get the eigenvalues as well. Here's an example. For the following square matrix, decide which, if any, of the following vectors are eigenvectors of the matrix and give the corresponding eigenvalues. Okay, that would seem like a nice little exercise. I guess one way to probably approach this is to multiply them all out and see if the result is a multiple of the others, some scalar multiple of the others. And if it is the case, then sure, they should all be of the same pair. Now, there's should be 3 of them. And so we'd multiply them out. Let's see if they probably do not even get into that. So we'd have to just multiply it out by hand. Now the result would be a matrix of this form. So let me see if I can. I haven't wrote on my pad in a very long time, so probably pretty sloppy, but whoa, see? I'm better off doing this in some technology program like one of those Octave or Python or R or something. So I'm going to multiply this out. So 2 times 3 is 6, 0, and negative 1. 6, 0, negative 1, that's 5. Now I do the second column. 2 times that, 2 times that, 2 times that, and add them up. 2 times that's negative 8. 2, that's negative 6. Negative 2, that's negative 8. And then finally multiply the last one. 2 times that is negative 12, 0, so negative 10. So there's what I got. That's what I got. Now, this doesn't seem to make much sense because when I multiplied it out, it's not a multiple. There's not a single number that I can multiply this by to get what I have there. So let's try another one. That maybe that was the one that may not even work. Let's try another one. See what happens. So I'm going to multiply this out, and again, when you multiply it out, you got to visualize this going on top of the other one, multiplying it across and adding them. You multiply each one by each one, and you do it for each column. So -1 is at -3, 0, 2. That's -1. Then I do the middle one. That's 4, 0, 4. That's 0. And then the bottom one. 6, 0, -4. 6, 0, -4. That's 2. These two turn out to be the same. If I multiply it by just a single 1, I get the value. So we'll stop right there. So I would say then that this is an eigenvector and the eigenvalue is 1. The first one I didn't know. It wasn't a multiple of that of the other one. Okay, so we're warmed up, and I'm going to come back on. And I'm going to stop it right here. That's a little warm up to the principal component analysis. Basically, some of the things that you should know going into studying the principal component analysis. I hope you enjoyed this video. Comment below if you want more info. We're gonna keep studying together, guys. So this is just the beginning.